Okay, let's get started. We have the roster sheet going on?
Yes.
Oh, okay, good. Thank you. So I see some of you made it back after our holiday last week. Not everybody, but most of you did, which is good. The important people made it back. There you go. People who are going to learn something made it back. All right, so moving right along today, we're looking at lecture number 5 and interface design. And I can warn you ahead of time, if you haven't looked at lectures 1 through 4, haven't built a class yet, haven't tried inheritance yet, number 5 is not going to make any sense to you because it builds on the concept again. So at this point, you should have hopefully compiled Hello World. Maybe would have done assignment number 1, but you don't have to at this point. And hopefully you were here or you watched the video from the last session. Last time we met, we did inheritance, and I went through a couple of examples. I put out 2 new videos on YouTube, tutorials 5 and 6. So we have an easy inheritance example, and then we have a more complicated inheritance example. I'm working on number 7, which was going to be even a more complicated one. And then we're going to have an interface design one that's going to come after that. And when I say more complicated, it doesn't really mean more complicated. It just means it's adding more features on it. So we have multiple different things being demonstrated. You know what? I am not wearing this. Yeah. Hold on one second. I don't know why. Is it a second ago I started thinking, where's the mic? All right. So we're going to go over a couple of examples and talk about the concept of interface.
Channel number 1, no?
And it is on channel number 1. Yes. Okay, good. So let's get started without any more delays. Now that we're technology oriented, and we got the mic on, the camera on, we're all set to go now. So the concept today on the menu is the concept of the interface. You don't actually have to use an interface, but it comes in handy, and you'll see why by the end of the lecture, why it's being used. The interface, by concept, is a way to describe what classes should do without specifying how they're doing it. It's kind of like the abstract concept that I talked about before. It says if you have an abstract method in a class, you have to make the class an abstract class. An abstract class is kind of like an interface, but it's a class. It's not an interface. And its purpose is to put placeholders in there. So you don't want to fill out the entire abstract class. Instead, you want to keep it abstract, which is a high level, kind of like we want this method, we want that method. And when we implement the functionality in the derived class that we create from the abstract class, that's when we add the behavior and we start adding functionality and things, which is different than the interface concept, but very similar. And this is where some students kind of mix the two concepts a little bit. So an interface is not a class, like an abstract class. So it's a little different. It has a set of requirements for a class that you want to conform to a particular interface. This is kind of like, if you're familiar with C or actually C++, this is like the .h specification and the implementation, the .c++ file. Kind of similar, but again, a little different as well. So the interface gives us, in this particular example, what we see here is public space interface, where normally we would say public class comparable, public class something. No, we have public interface. So we're creating an interface, which means we can't make instances of this. It's not an object. So class is the implementation of the object, if you remember that. Interface is not a class, not an object, but it's an interface to an object. So we'll see an example and make a little bit more sense. And here we have a method that says compare to, takes an object, another object. Don't worry about the code at this point. Just think of it, looks like a class. The only thing different is we call it an interface. We put methods in there so that we can put, almost like abstract methods, we can put placeholders for information. So this requires that any class implementing the comparable interface contains a compare to method. So everything, kind of like the abstract concept, everything that you're putting in to this interface is required to be implemented if you're going to use this interface. And I think what it does is it kind of like sees into the future a little bit. The interface kind of like projects into the future and says, we're going to be implemented, and this is how we're going to be implemented, and this is what we require, and this is the vision or the concept. that we're looking at in future classes that are built from us. So this method in this particular example must be, and it must take an object parameter and return an integer, because of the type of method is int or integer, and the parameter, if it had 2 objects, it must take 2. If it had 1, it must take 1. So you can't deviate from the interface specification that's created. Okay, so we have declarations. So the declaration consists of a keyword, which is the word interface, its name, and then the members that are associated with it. And here we have public interface comparable. And so we're taking, and it has to be public because we need to be able to access it. We need to be able to change it. If we made it private, it really wouldn't be an interface. Because from what we know about private, if it's private, it's stock. You know, we can't build an inheritance. And interfaces is part of the inheritance structure. So similar to classes, an interface can have 3 different types of members associated with them. Those would be the data members, or the fields, if you like to call them that, or variables, if you like to call them that, methods. And then also nested classes and interfaces. So you can put an interface inside of the particular interface. You can put a class inside of the interface. So it basically has pretty much the same types of members as a regular class, but it's not a class per se. Okay, so class members, we have constants that we can declare inside of the interface members. I went the last 4 weeks saying class this, class that. Now, okay, interface, not a class, interface members. So the interface can define named constants, which are public, static, and final. So we have the modifiers are omitted by convention because they're going to be automatically set because we're creating an interface. So we have some built-in kind of rules or structure that goes along with this interface that we're sort of working with. And it never contains instance fields. It always has interface-defined constants. So here's an example here. All of the named constants must be initialized to something. Otherwise, we can't set a value. So here we have an interface verbose where we have integer silence, terse, normal, loud, I don't know, verbose, whatever. I guess that's wordy. I guess that means wordy. And where we have it initialized. So we have to initialize the named constants that we're using, but we don't have to follow with public, private, protected, static, nothing. We don't have to actually specify the access methods because they're going to come in public, static, and final. I mean, they're going to basically come in that way for us automatically because we're going to use this as an interface. And then now we have a method down here, set verbosity, that takes in an integer level. And then it's going to basically set or get, integer get, it's going to run a method. So it's going to basically run something. So the method in there would have to be implemented if we were to extend the class from this. So let's talk a little bit more about the methods. So they are implicitly abstract. So as I mentioned before, the abstract class is there because we want to require that method be implemented. Well, same thing, but you don't have to say abstract. It's going to be there automatically for you. So it's omitted by convention, but it's implicitly set that way. So every method you put in there is going to be abstract. So every method declaration consists of the method, the header, and a semicolon. So in here we have the method, set verbosity. We have a semicolon at the end. We don't have opening and closing brackets. It's kind of like, if you're familiar with C, going back to something you might be able to relate this to, sort of like a prototype, function prototype that you would put at the front of the program. Same concept, actually. Very similar. So they're implicitly public. They have to be public. As mentioned before, you can't make it private or protected. And that's also admitted by convention. So back here we have a void instead of public void. If you put that in there, I don't believe the compiler is going to complain. It just doesn't mean anything. It won't work. I mean, I think if you put like private in there, it might actually throw an exception. But I haven't tried it. So they are implicitly public, omitted by convention, and no other types of access modifiers are allowed. Okay, so yeah, it would probably throw an exception for you then. It wouldn't make any other sense anyway. So they can't be final nor static because they're interface. They're not class related. So static would mean nothing, actually. in terms of the class. So modifiers of interfaces itself. So an interface can have different modifiers. So it could be public or package default level, which is what it ends up happening. So if you leave it out, it becomes public or package. It could be abstract. All interfaces are implicitly abstract, however, so that's also admitted. So to create an interface is actually quite simple. It doesn't really have anything in it. I mean, it doesn't really have as many options to mess around with. So, okay, so to implement it, let's take a look at this. Implementing interfaces in a class. And I have an example I'm going to actually go out to and show you in Windows that will kind of put it together. And I'll show you where to get those files as well off of the Behaker website. But you have two steps to make the class implement an interface. And you want to declare the class that it intends to implement the given interface by using the implements keyword. So if you remember anything, remember extends creates inheritance. So you can derive a class from a base class by using extends as a keyword. If you're going to use an interface, then you use the word implements. And here's the interesting thing that confuses everybody. You can implement multiple interfaces, but we only go class by class on extending. But we can implement interfaces from 5 different interfaces or 6, or as many as we want, which is interesting. That's why, and you just separate it by commas. So implements comparable, comma, implements something else, comma, or, actually you don't put the implement. Implements this A, comma B, comma C. You implement all of it. So we have the keyword, new keyword. So class employee implements comparable. And so we're saying that it's going to basically look for comparable as an interface. Has to be in the same location or same package, blah, blah, blah. Same thing applies if it were a class. It has to find it. You could supply definitions for all methods in the interface. In fact, that's step number 2. So we have public int compare to inside the method of the interface, inside of the class employee, we are implementing. So if you kind of think implements, meaning you're providing the method body for the interface that you've created, and you start actually kind of thinking it in terms of how the words are being used to describe the concepts, it makes a lot more sense, actually. It's kind of natural. That's why I say they're not really that hard to think about. But there's a lot of Java programs that don't like the whole concept of an interface. And they've never even used one because they're afraid of what, I don't know what they're afraid of, seriously, but it's not that bad. So we have the method body here. So all of the methods in the interface need to be implemented, otherwise you're going to get an error. Note that in the comparable interface declaration, the method compare2 is public implicitly. The modifier is omitted, so in the interface it was omitted, but in employee class design, you can't omit the public modifier. You actually have to put it in when you implement the method in the class that you're using the interface with. That's a lot of words. So otherwise it's going to be assumed to be a package accessible versus public. So you actually have to say public if you're going to use public on it. Or you can actually change the access method. It doesn't necessarily have to be public. So if a class leaves any methods of the interface undefined, the class becomes abstract class and must be declared abstract. Oh, so now going back to, yes. It's just a parameter that's being passed to the method, and the method itself was defined as an example here, where we have a public interface comparable, and we were just saying this particular method is going to take an object, another object.
And then the other is the object of employee class?
It could be. We're just going to pass an object in as a parameter. You could change this here and say integer I. Don't worry about the object concept at this, because we haven't actually, you're right, we haven't actually seen very many examples where we're passing objects, but we're getting to that. So probably just exchange that with anything you like. String, or integer I or something. It's taking a parameter. And believe it or not, you can't overwrite it. So if you're using this interface, in the implementation, you actually have to provide the same header the same method header, which means it has to take object, other object. And then you fill in the method body. And then all of a sudden you basically have implemented the interface. So you can actually build an abstract class from a class. You can create an abstract class from an interface. You can use one without. You can basically use abstract classes without interfaces. But you could build interfaces as a level underneath, let's say the abstract class if you wanted to in this case. And you do that when you don't know, when you want to include the functionality but you're not quite ready to implement it yet. And some of you at this point start thinking, well, why do I want to put it in there if, could you shut the door, if we don't want to implement it? Well, the point being you're trying to set a foundation for a structure. And you want to make sure you're kind of accounted for all of the parts and pieces, whether you're going to use them now or into the future. So although we gave humans arms and legs, and we may not have defined how long each section of the arm is, or we may not have, but we've decided that a person or a human is going to have these features. And then we can implement them as we get further down the road and transform the object into something that we want to use. So a lot of it is just like, I hate using the word placeholders, but it is kind of like a placeholder. So, okay, and the last item on the bottom, a single class can implement multiple interfaces and just separate the interfaces by the comments. So here we have the employee, this is what I mentioned before, where we have class, employee, implements, comparable, comma, clonable, which is another interface. These are just interfaces that were created. So you just separate them out by commas. But we know we can only extend a class, from a base class, but we can implement multiple interfaces, which means we can bring together a bunch of functionality and make actual multiple, one wouldn't really call it multiple inheritance, but it kind of simulates, it kind of creates a more of a multi-interface environment, let's call it that, where we can bring in things from other sources. So let's instantiate some properties of interfaces, because we can use an interface inside of a class. We can use it on its own. Interfaces are not classes, so we can't make instances of them out in public, out in the main driver program. And we can never use a new operator on them. So we can't say, as an example, comparable x is equal to new comparable. We can't make instances of these objects because they're not objects, which kind of is another mistake some people do, because it looks like an object because we're creating it, but we're using the word interface instead of class. So it's basically only in existence for our hierarchy, for inheritance. So unless you're using inheritance, you shouldn't be creating interfaces, because it makes no sense, essentially. You're just doubling your work. Which is another question, actually, some students usually come up with is, why are we doing this anyway? Because it just makes more work for ourselves, right? No, actually, it lays a better foundation for inheritance. And as we'll see in the coming slides, it gives us some more capabilities that we wouldn't normally have without it. And we'll see the benefits coming up as soon as you get through the labor of how to do it, how to use it. So you can still declare interface variables, and here we have that check mark. This means it's okay. Unfortunately, it should have been like to the right or to the left of the word instead of on top of it, because it looks like it's wrong. So the top example is, no, you don't want to make a new, you can't make a new instance of an object, of an interface. It doesn't exist. But you can still declare interface variables. So we have comparable x. We wouldn't do that out in a main driver program. Rather, we'd do that inside of a class that we're implementing that's using the interface. We can use multiple interfaces inside. So we might want to create a variable that represents it and then call the variable. Just the same way as we would use variables in other instances. We'll see an example, actually, how that works in Windows. But you must refer to the object of the class that implements the interface. Here we have x is equal to new employee. We have class employee implements comparable. So we have x as a comparable type object. So it's basically used as a variable. And then we've taken x and had it equal to a new employee. So we're not creating a new comparable object. We're creating a new employee object that implements comparable. So, are we all good so far? Okay. Oh, good. Okay, good. I'm trying to purposely go slow through this, because if you don't get the concept at all, it's really hard to build on this. It's really hard to use it. All right, so let's extend some interfaces. Interfaces support multiple inheritance. This is where we get multiple inheritance. Okay, so far I've been saying we've had single line inheritance. Well, we have multiple actually with interfaces. So an interface can extend more than one interface. So we have more than one that we can put into it, and we can extend more than one. So we can nest the interfaces as well. Super interfaces and sub interfaces exist just how we have classes. So public interface, serializable, running extends, IO serializable, comma, runnable, comma, almost anything you want actually out of that. So we do have multiple inheritance. It's just done a little bit differently than it is done in other languages. So let's talk about constants. So an extended interface inherits all of the constants from the super interfaces. So now I got a bunch of, well, we talked about constants. That's what I'm talking about with that integer. Actually, I can't remember what we had in this class. Oops, I think it was right here. Nope, it was in a previous example. Here we go, silence, verbose. Actually, this was a different class. We didn't have constants in our other one, but we can. I think the example actually creates some. So all of those are inherited automatically, and from the super interfaces. So just basically take the word interfaces and substitute class, and it's everything you knew about sub and super in terms of classes applies to the interfaces. So take care when a sub interface inherits more than one constant with the same name. So if you could imagine the concept, and this is what happens with classes and multiple inheritance, what method from what object are you talking about? Because sometimes you have the option of using the same name in multiple interfaces. Then you've got to basically resolve which one you're actually talking about. So if you do that, then on the interface itself, you can resolve it by going back and using the dot notation. Or you can actually this is a better example here, specify explicitly. So here we have an interface that inherits two or more constants with the same name. And in the sub-interface, we've explicitly using the sub-interface name to refer to the constants of that sub-interface. So we have interface A, we have interface B, and then we have interface C that extends A and B. So now this is where people who weren't okay are not okay at this point, because what do we have? Extends A and an interface can inherit from interfaces and can use them. So here we're inheriting A and B. Excuse me, we're creating C as a super interface to sub A's and B, or the other way around, sub interface to supers A and B. So because you have to turn the hierarchy upside down. So C, every object interface of C also is an A and a B. So inside of the interface here, we have A dot value, B dot value, because we have value used both in A and B. This is probably the most confusing part, I would say, in terms of those constants. Because then you start looking at the interfaces and you're like, well, why are we doing this to begin with? And then after you figure that out, then it's like, well, what value of value? How come I'm getting the wrong value? How come it's coming out with the wrong number? Because now you've really opened up the door to multiple sets of variables, multiple sets of methods, which kind of can become confusing, but it's very powerful. If you could probably see how feature-rich this actually makes the language. All right, so we specify out A dot, and now you're going, well, they're not objects. No, but you're actually using this kind of like a static variable, sort of, but it's not. It's tricky. All right, so if a super interface and a sub interface contain two constants with the same name, then the one belonging to the super interface is hidden. So you're overriding in a sense. So in the interface itself, you access the sub-interface's version of the constants by directly using its name. And then you can access the super interface version of the constants by using the super interface name followed by a dot and then the convention here. So we've seen this. We've got interface X, interface Y that extends X, and then we have value and value. So we have value.x. So outside of the sub-interface and the super interface, so outside of that, you can access both of the constants by explicitly giving the interface name. So we have y.val, and we have y.sum for the particular y interface variables. So same kind of dot notation you're familiar with, but it's used with same kind of rules apply. It's used the same way with interfaces, essentially. And this is why I said it's probably good to have hello world written at this point and know how to call methods from objects. Otherwise, this is going to be a total loss. So, hopefully you're following me so far. All right, so just a few more tedious little details to think about. So when the super interface and the sub interface contain two constants with the same name, let's see, and a class implements the sub interface. The class inherits the sub interface version of the constants, which you'd probably naturally expect, and it's static fields, so it gets everything. So their access follows the rules of the class's static field access. So the access basically follows, and the same thing applies, essentially, from the inheritance. So here we have class Z that implements Y. And inside the class here, we have Z.value. And we have outside the class, we have Z.value, and we have the same number. So static works the same way, long story short, as well. So it kind of reinforces as well your understanding, hopefully, of what the static the static term actually applies to. So object references can be used to access the constants in terms of object references. So as I mentioned before, can't make objects out of interfaces, but we have object references that we can actually access the constants from. So sub-interface version constants, this is like a tongue twister, are accessed by using the object reference followed by the dot followed by the constant name. So here's our example where we've got z v equals new z. We're making a new instance of the object, calling it v. It's really a z. And then system.out, we're printing v.value from v, which is the object. And so we're using the object and we're accessing value from the field inside of the object, from the interface. So it works the same way as a class would, actually. But you can't make an instance of an interface, but it works. Everything gets inherited. So just think about inheritance and go, well, that's what inheritance is all about. Everything transfers. So that's everything you ever wanted to know. In fact, it's the same rules that apply towards fields or data members. So the member functions are the methods. In terms of extending the interfaces, there's a few kind of important things to look at. In terms of classes, when we extend them and we create inheritance, we build, we override, we overload. We do all sorts of different things in terms of the functionality so we can change it. If you declared a method in a sub-interface that has the same signature, which means it takes the same number of parameters, follows the same format, as an inherited method and the same return type, then the new declaration overrides. Same thing we have with constructors when we start overriding them. If it's the same signature, it's going to override it. So it's going to override the inherited method in its super interface. So in terms of the interface inheritance, it kind of works the same. So if the only difference is the return type, then you're going to end up with a compile time error. Can't change the return types. You have to change the entire method if you're going to do it, which means you're probably not going to override very much. You're probably going to leave it alone, which is kind of the intended purpose of the interface, was to set the design, to set the interface, to keep things consistent, theoretically, in concept. So an interface can inherit more than one methods with the same signature and return type, as we see, because we can implement multiple interfaces and then also inherit them. So the class can implement different interfaces containing methods with the same signature and the same return type. So the class can implement whichever one it wants to. So overriding in the interfaces has no question of ambiguity because they're all different in terms of the override, because we can't. So the real behavior is ultimately decided in the implementation. And so when you basically take the class and implement it, then you make the decisions as to what part of the interface you're going to borrow from this interface, from that interface, and you put it all together, and the ultimate decision is made in the class structure itself, or in the class implementation. So methods with the same name but different parameter lists are overloaded. Well, that's no biggie. It's the same thing that we saw with the constructors, overloading constructors. So a lot of the same concepts actually apply. And now you're probably wondering, well, why use interfaces? So this is the example I kind of want to show you to put everything together. So we have shape, point, circle, and cylinder, and we have test.java. So the usefulness of interfaces goes far beyond the simplicity of publishing protocols for other programmers. That's pretty much the focus I've been telling you so far. When I say publishing protocols, it means you're kind of laying the foundation of how you want the structure to work. Any function can have parameters that are of interface types. Any object of a class that implements the interface may be passed as an argument. So now we have multiple uses of the class. So let's take a look here, actually. I'm going to, at this point, stop the PowerPoint, go to Windows. But before I do that, let me show you where these examples are coming from and make a note about something else. So if you go in the weekday classes section, and you go under the object-oriented design in Java, at the top, I don't know why the rest of the page didn't populate, but it's probably a slow access, slow connection. There we go. And if we go into course materials, and hopefully this will come up. Yep, there we go. So if we scroll down to the bottom, now a little note actually, because I've had some people ask me, where I've got the assignment number 1 has no support files. Assignment number 2 works with these 2 files as support. It's showing you output. It's showing you a test program that you can test your methods with, so you don't have to write the driver program. On assignment number 3, some of the files, for example, this rat number, rat string, tester, whatever, are support files showing you an example. You may or may not need to use all of the Java files. Think of them more. In fact, if you read the instructions, it'll tell you, if you're going to do it this way, then you would probably want to implement it this way, and here's a file that has it this way to show you it as an example, because it's more of a learning / assignment with an interface to it that you can actually kind of play with. But don't feel like you have to understand exactly what all of these files are doing and what's going on. But the support files are going to make your life a lot easier. If you actually take the time, there's only 5 assignments here. If you actually take your time and actually read everything and try not to just fake it and just kind of, try to actually do it, it's pretty educational. So the assignments are kind of designed to teach you the technique while you're doing the assignments, is what I'm saying. So download the support files that go with it. Long story short. Number 4 and 5 don't have anything. Number 5 is, well, we're going to talk about applets soon. Okay, what I really wanted to show you was this section down here where it says lecture samples. And this is from last week. Actually, this is from this is the hello world from the beginning. I put the inheritance example 1, inheritance, this is last week's files, or the week before. What we have is chronologically all of the files that we're using. So we have here shape, point, circle, this is from today, and lecture 5. I've tried to label some of the stuff with, I didn't put lecture 5 in front of shape, point, and whatever, but in the lecture it mentions the file. If it does that, always go to this directory, you'll find the files that it's talking about. Okay. And they're just text files. So when you click on them, you can download them, use them. So. And you can't use that system to upload your assignments. I think we're going to do a I2 EMS update soon, aren't we? I don't know. Eventually we're going to want to get that set. All right, so here's what I did, and if you were here last time we had class, you can open up and create, and I assume nobody wants to see this because I've already shown it to you guys, how to create a generic project in Eclipse and load the files in by importing them. Does anyone want to see that? No? Okay, good. We've already been through that. Okay. Well, it's hard to tell. So let's take a look, and I want to take a look at shape because shape is the interface. And I want to make this a little bigger. Let's make this bigger. All right, here's a real life. Oh, that's big. That's big. Okay. And here's a real life example. It's shape.java. It is an interface. So it's definition of an interface shape. Because if you think about a hierarchy, we have the concept of a shape that we're going to interface, that we're interfacing into different types of shapes. So we can make a circle, a square, different shapes as a concept. Kind of like how person turns into employee, turns into boss, and then we have dependents that are part of. Actually, if you haven't looked at that example, you'll see how a class can be used inside of a class because we created an array of dependents inside of the employee class. So it kind of gives you a little bit of exposure about that as well. But we've called them abstract. Doesn't really matter. We didn't have to. We could have just said, in fact, we could have left off public as well and just put double area, double volume, get name. The example actually comes from the book, an older version of the book that I highly recommend if you're having problems. The Deedle and Deedle text, you can see the reference for it. In fact, you probably could just cut and paste this, put it in the web browser, and you can probably see the exact book it came out of. That's where you go for additional help if these examples are not working for you. Let me make it so small, it was almost too big. Okay, so. All right, so we all good with the concept of the interface? Doesn't really have anything, it doesn't implement anything. If you have constants, you put them in here, and you actually have to define them as well as initialize them, so you have to give them a value. So if you said, pi, let's just say 3.14. Actually, so remember that part. Otherwise, what ends up happening is students, they put constants in here, but they don't give them a value. And then it's like, oh, wait a minute, it can't be used. It's not going to work, essentially. You probably end up with an error. Okay, so going from shape, let's try point. No, let's not try. Let's try circle. Let's go to circle next. No, let's go to cylinder. Let's go to point. Let's go back to point. All right, full circle. I was trying to find a simple one. Okay, so now we have point. So what's a point? Well, it's defined by an xy coordinate. So here's the interesting part. This is the part you just have to kind of memorize, I guess, or kind of get used to. We're implementing shape. We're extending object. We could have extended, if we wanted to, another class outside of object. If you remember the hierarchy, object, it's the root of everything. If we want to start using objects that are just generic object inside of the implementation, we actually have to extend from object. If we actually leave it out, it still works. It still works, yes. Yeah. So you could, if you don't like this, you could remove it and say that class point implements shape, and the program will compile and run just fine. But I put this in here kind of like how I put the this and the super to show you that some people like to do this. But object is the highest in the hierarchy. So anyway, Deedle and Deedle, the text, he always extends object in inheritance because he's trying to enforce the concept that everything comes from object. So whatever. It's not necessary. All right, so we have protected integer x and y. These are coordinates. We all know what protected means. Yeah, so they're private everywhere except for inherited classes. We know we're going to inherit from point because we're going to use point to define a square. Hopefully, we're going to use it to something else. So I'm kind of reviewing some of these concepts because it's been a while since the last time I've seen you. So we have two little integers. They have no argument constructor here. Just says point. And the point's going to be set 0, 0. And then we have a constructor that takes on in x and y coordinates. So just to review the constructor concept, we can have multiple constructors. And we have a constructor that's calling set point, a method. That actually is kind of common, actually. If you build the functionality in, so you got set and get methods, accessors, modifiers, because all of your data is going to be private or protected, depending upon whether you're going to use inheritance, you're not going to be able to access any of those variables outside of the class, hopefully. If you're using this type of technique, you already have a set point. Why reinvent the wheel in your constructor? So you can create your constructor to call your set point function, or method, I should say. The other thing a lot of people actually kind of do is just call the method right after they create the object instead of doing the constructor, which it goes back to another point that I made earlier on in the course, meaning all of the functionality should appear in the class, just a few lines of code in your main driver. So if you have to create an object and then call a set point method on that object in the driver, it's not as efficient, it's not as desirable Then if you did it in 2 steps here, had the constructor call the set method. So you can set x and y coordinates of the point using the set one. We didn't put the this dot anything in there. In fact, that's the other thing Doodle doesn't do. He extends object, but he doesn't put this or he doesn't use super or this for anything. So, but you don't have to. I mean, in some cases it makes sense if you want to call constructors of an inherited class, But anyway, get coordinate x, get the y, convert the point into a string representation. Pretty trivial. We did a string to string method, and coming from object actually. Calculate the area. So here we have our public area. This is our implementation from our interface. If you remember, the interface had area, volume, get name. So it's very common to group the method implementations together. So again, another style thing. I don't have. I mean, this goes above and beyond the implementation, and it's not even required. But mostly, you'll see notation that says interface shape, and then underneath it, a comment that will say interface shape, and then underneath it, you'll see all of the shape methods implemented, and then you'll see interface, whatever the next one is, and then you'll see all those, because then you can kind of figure out where it came from, and it kind of documents your logic, sort of. So I don't know. So it's standard. I wouldn't say convention, but it's like a best practice, I should say. So, all right, so it's kind of trivial. So there's point takes and implements the shape. And so let's see, we got actually I think I have them all open. So we'll go to circle next. So circle extends point. So this is a inheritance, straightforward inheritance, but it works with the interface as well because point implements interface. So circle that extends point is going to also implement the interface. So we have circle extends points. We have again, I don't have to go through protected. You already know that part. We have a no argument constructor, the circle. Why do people put that in? It's kind of like, again, another, if you don't have to put it in there. There's no requirement to have a default constructor like that doesn't take on any parameters. But again, it goes back to best practices. People put that in there just to say, if they want to add it in the future, they could put some code in there. So a lot of times you see empty methods like that for no reason. But this one actually sets the radius. So it implements a call to super class constructor here if you wanted to implement a call. The constructor here taking on the radius because now we have radius. We have the x and the y coordinate because we're implementing we're creating a circle as a shape concept. What do we have here? So super. He does put super in here. So super the x y. So supering back to initialize the constructor for point, and then add the set radius to it. Same concept as before. We have set radius down here, which sets the radius, and we have a get radius. And lo and behold, we have a area. So calculate the area of the circle, which is going to be different than calculating the area from a point, which is not really possible. So we're doing a little calculation to do that. Converting the circle to a string again. Oh, little typo, don't worry about it. Kind of the same concept as we did before. And then the get name. Same as the other interface that we had that had a get name for point. So we can pretty much implement the same behavior, essentially. So we're building on the concept and creating a circle from a point. And then we have the cylinder. So I guess the cylinder would be more complex. Cylinder extends circle. So this also kind of shows you the inheritance part of it. Again, trivial, no constructor, default constructor. Another constructor that it takes on, now we have the height, we have the radius and the x and the y. And you're wondering, why in the world would anyone do this for a circle, for a shape? Concept is that this is a very small example. Imagine like a big accounting program or something, or imagine a payroll program. It becomes a little less trivial at this point, and the more structure you can actually put into it, and the better you can lay out the class structure, then you can divide out the behavior. A point is a point, right? A circle is a circle, and a cylinder is a cylinder. They're all shapes. They're all implementing the same concept, but they're extending behavior on each other through inheritance to give you that object hierarchy, if you want to think of it that way. So we set the height of the circle here. Let's see. Get the height of the circle. Calculate the area of the circle. It's kind of the same methods as before. Now we have calculate the volume of the cylinder. And it's like instead of the area, because the area was for the whatever we had there before. It's the surface. Oh no, it was the circumference. I don't know what it was. Anyway, I'm hopefully you're getting the point. It's all the same stuff. It's all implemented differently. It's implemented differently for a cylinder versus a circle versus a point versus a shape. The test program. So we have 1, 2, 3, 4. We have one interface with 3 classes that are built in a hierarchy. And as I was mentioning before, the driver program is fairly small. In fact, if you pulled all the unnecessary comments out, it would be like 5 or 6 lines of code, actually. So this is what your programs should look like. Drivers should be extremely small. Classes should be big. And classes should be inherited from each other, like extending behavior. So you're dissecting out an object that is an object of a particular type. Okay, so going back to some of the other things we were talking about in the prior to our day off, we have imported Java text decimal format. We could have just used an asterisk, but we went very specific with this one because this is really the only method we're going to use. Java extends package swing. Actually, I don't even think we're using any swing. Oh yeah, we are actually, but it's not going to draw anything on the screen. We're not actually going to do any graphics on this. We'll learn a little bit more about swing later on. So in our class test, which is our driver program, we're creating a variable for precision 2, and the variable is an instance of an object, decimal format that we created using this imported package and class. And out here in void main, or program itself, we're creating shapes. So we have a point, that's a new point. We have a circle, that's a circle. A cylinder, that's a cylinder. We're creating a shape array. So shape array of shapes, new shape, which allows us to take and a subclass point object, a subclass of circle, a subclass of cylinder. So we have an array of shapes that are points, cylinders, and circles. And then we're just printing some stuff to the screen. We're getting the get name. We're running the get name method to essentially print some stuff to the screen. Or actually, no, this is just printing the length or something. So anyway, if we run it just to test it, make sure it does run. And if we run the example, run as an application, then we should see on the bottom. Oh, it's loading. Test run. At the bottom of the console, that was not shown in the beginning there. All it's doing is essentially printing out the whatever the system out was basically designed to print out on each one of the different methods. So we have a point, we have a circle, and we have a cylinder with all different characteristics that are associated with it. So it's just basically another example that shows you the inheritance, shows you the use of the interface, hopefully, in terms of how to put it all together, I should say. So it's not a bad starting point, actually. If you're completely confused, download the example, put it in, go through line, start removing stuff, start playing with it, and then it'll easily come together for you. So. Okay, a little bit left here, a few other comments to make. Let's see. Okay, marker interfaces and object cloning. Kind of go along the same interface kind of concept. So marker, tagging interfaces themselves are neither methods and they're not constants. So its only purpose is to allow the use of an instance of in a type inquiry. So we could say, if you remember the instance of method call, we could say, what object are you? Are you an instance of this? If you're a circle, are you an instance of shape? Are you an instance of point? And then it comes back with yes or no. And we kind of check to see self-identify objects. So that's actually referred to as a marker or a reference. And it's just terminology as well. So clonable interfaces. is an example. So we can clone objects in terms of what they are, and we can make objects into other objects. So we can, in terms of the object clone, a clone method returns a new object whose initial state is a copy of the current state and the object on which the clone was invoked. So it's like making a copy or a clone. Same English translation of the word clone used in other situations. Subsequent changes to the new clone object should not affect the state of the original object. So instead of copying one variable to another, we're cloning the variable, which is similar, actually, in concept. 3 factors in writing a clone method. So the clone method itself, and then we start looking at memory locations and references to information that are part of the object. And the reason why we're doing this, and it's kind of not as trivial as, let's say, copying a variable or copying an object to another object, is when we copy, we waste. We don't really share reference to memory. We've basically taken and duplicated efforts. So cloning is similar, but it's slightly more tricky in terms of the way it's implemented. The empty clonable interface. So what we have is 3 factors in writing the clone method. The empty clonable interface, you must implement it to provide a clone method that can be used to clone an object. So you have a clonable interface that you're using to implement it. And so you're manually there's actually no feature in the language that does this for you automatically. Although some object-oriented programming languages do this, built in with keywords. Instead, you're implementing the concept of creating a clone of an object by playing around with the methods and the way that you're creating them, the way that you're using them. So the clone method implementation by the object class performs a simple clone by copying all the fields of the original object to the new object. So it's kind of like taking all of the data members and transferring all of the data so it's equal. And that's how we get 2 objects that are the same. It's like 2 people that are twins, born on the same day, have the same characteristics, same concept, cloning. So now if we could just clone ourselves, like that movie Multiplicity, I have clone number 1. Those clones degraded, those clones got worse. You just started making copies of them. These objects here, they clone perfectly. So we've got cloning down. So there's no biotechnology going on. No bio, whatever. Anyway, so the clone not supported exception. I'll say, wait a minute. Okay, so the clone not supported exception, which can be used to signal that a class's clone method should not have been invoked in particular situations, can be essentially thrown to say, no, you can't make a clone. That it's not going to work. So there's an exception, actually. Part of the exception handling actually works with that. So here's some details about object cloning. The object class, when we saw the object class, we extended from object in that example that you just looked at, provides a method named clone built in. You actually have to call it, though. That's why I said it's not an automatic thing, but the environment's set for you to implement it. And the clone method of object performs a simple clone by copying all of the fields of all of the original objects to the new object. So we call, .clone, and we create that new instance of the object that's a clone. And it works for many of the classes, but may need to be overridden for special purposes. It's not 100%. Sometimes you do have to override it in order to get things working. And when you have to override it, this goes back, and for all of you C++ programmers who dealt with shallow copy versus deep copy, and pass by reference, pass by value, and all of the dynamically allocated memory concepts. The concepts and problems still exist in Java, but there's more automated features for you to use, and there's more different techniques. It's implemented, but you have less control over it, and there are different ways of dealing with the issue. So if you remember, if you have a C++ background, you wrote a destructor, and you wrote a copy constructor. Cloning is equivalent to the copy constructor. Because the only constructor we have in Java is the default constructor. We don't have a copy and we don't have a destructor. Because we got rid of the destructor completely because we have automatic garbage collection. Copy constructor is what we have to create manually when we clone, and we do that by creating shallow copies or deep copies. we get a shallow copy automatically. Same concept is true. And if you don't know what I'm talking about, I'll just briefly explain the difference between shallow and deep. A shallow copy takes something that's being used as a value and copies it to another variable. When I say integer I, integer j, I is equal to j, I've done a shallow copy. When I create memory and I say new something in C++, that created what was called a memory accessible reference. New and delete was used to allocate and deallocate memory programmatically by the programmer. It's done by the Java JVM for us automatically when we say new, but the concept is still doing it. It's still allocating that resource. And we go and instead of using the value that we're putting at that memory location, we're using the memory location. So if you think about the concept, we're juggling around memory locations. Same thing, same way we use pointers in C++. If you're familiar with that concept, it's the same as using a pointer essentially, because we're just juggling the references to those memory locations or the addresses of those memory locations. So when we make a deep copy and a copy constructor in C++, we take and we copy. We go new, this, and we make a physical copy of all of the referenced memory instead of referencing the original memory. Because if you clone an object, if you think about the concept, if you clone an object, it's going to use what? The original object's memory to start out with. It's going to get a copy of it, and then it's going to be at a totally different memory address, memory location. If there's memory that the original object was using, it's not going to get copied. It's not going to get created. It's not going to be used. So we make a deep copy to duplicate everything, essentially. And we do that in terms of the design of a method. So we don't have a constructor that does it for us, though, which is, I don't know why they didn't have a copy constructor. Instead, we have a method. But if you think about it, copy constructor is just another method anyway, right? I mean, it's just a way of implementing it. In fact, you don't have to use the constructor concept at all. You could just create methods if you wanted to. But nothing's going to happen automatically for you. That you're not really utilizing the features. Okay, let's see if I butchered this completely. Let's see, go through the slide, make sure I didn't, see what points I missed. Let's see, shallow versus deep cloning. So now you know, hopefully, kind of like the concept of shallow versus deep. Shallow cloning, a simple field by field copy. So it's like variable by variable copy. Might be wrong if there's a duplicates a reference to the object that shouldn't be shared. If an object is referencing something, you might not necessarily want to make a copy of that. And you actually kind of have to think out of the box a little bit and think about an object that might actually use another object. Going back to, let's say, dependent employees that have dependents, and you copy the employee, do you also copy the dependents that are part of the employee? If you just copy the employee, you might not get references to those dependents that are being used, that were allocated in terms of objects that were instantiated inside of that other object. And that's just one example. There's actually a couple of other scenarios that happens with. So here we have public class integer stack that implements clonable as an interface. And we have an array buffer. We have a stack of integers. So some code in there. We have the original. We have the copy. And the original, the copy is just a sheer copy of the original. It's just this concept of the simple fields being copied, the data members being copied. In our deep cloning, we would have cloning where all of the objects reachable from the object on which the clone is invoked is copied. So if we had a case where we had employees that had dependents, and we created a new employee object, and we created dependents with inside of other objects, and we did a regular old clone without doing a deep clone, we wouldn't get the dependents. Here we're going to get the referenced objects that that object is referencing, which are all of the dependents. So we would get copies of that as well. Why do we want that? We may not want that. If you think about it, if a dependent is a dependent, if we had, let's say, for example, now this is thinking extremely outside of the box, but we have parents, mother, father, one kid. If we wanted, both of them were employees, but they're both sharing the same child. If we did a deep copy, we'd have 2 children. We don't want 2 children. We only want 1 child. See, that's why I say it gets kind of like multiplicity. Start creating new people. So. And we may not in that particular case. So that's why we have a choice. We don't have to copy the referenced information, or we can just go ahead and do a straight copy of it. Okay, so that didn't take you over the edge. The rest of this will. Okay, here we go. If you decide that a class needs a deep cloning, not the default shallow cloning, so just remember everything by default is the same thing as C++. It's a shallow copy, unless you create a deep copy. Then the class must implement the clonable interface. So if you want to create the deep copying, you implement clonable. And clonable gives you that capability. So clonable interface has neither methods nor constants, but makes a class as partaking in the cloning mechanism. Makes the class. So you redefine clone method with the public access modifier. And I do not have an assignment that actually has you make a clone. In fact, usually you won't see this implemented very much at all. In fact, people just run and hide from clones and not even use it. In fact, a lot of people don't like to even extend object. The Deedle and Deedle text actually has a really cool clone example in it as well. If you have one of the, that was an old version of the text too. So I'm pretty sure you kept it because it's a really decent example. So let's say if you just have the class needs a shallow cloning, you still need to implement the clonable interface. You redefine clone to be public, and you call the super.clone from the super object, from the one that you inherited from. So interfaces and abstract classes, moving right along to a little comparison as I started out with to begin with. Why bother introducing the two concepts, the abstract class and the interface together? In fact, that's what we saw in that example that I showed you. And here's the source for it. We have abstract class comparable. We have public interface comparable. We have class employee that implements comparable. Here we have class employee. Then it's the same concept, kind of. I mean, it's very similar, whether we're going to extend or we're going to implement. So we know we have to use extend if we're going to create a class from it. Implements if it's an interface. But why bother? Well, a class can only extend a single abstract class. You can't take more than one class, but you can take more than one interface. So essentially, you can skip everything I said today and think about interfaces just like abstract classes. Everything you know about abstract, same concept. The only difference is on this slide right here where it says you can take and you can implement more than one interface, but you can't implement more than one abstract class. That's how you get around, and that's how you create multiple inheritance. People don't like multiple inheritance because it gets confusing, actually. It's only as confusing as you make it, though. If you map out the concept, and this is where, if you start thinking about it, where programming and object-oriented design are kind of like at extreme opposite ends at this point. Because there's a concept of creating a really good design, and then there's the nightmare of having to implement that design. And the nightmare is if you actually have a decent object-oriented design, you pick up one of these rational rows tools or something, or you follow UML design, then you have interfaces. Then you have, classes that are inheriting from other classes, and you have all of these things. This is just the way you programmatically implement it. So you don't want to just go, every program I'm going to write is going to have an interface. It's like, why? So this is the time in the course where it's like, okay, now I can't teach you any more programming. I have to teach you object-oriented design because now you need to know when to use an interface and when to use an abstract class and when to inherit. Why you inherit if you don't have to, kind of thing. So what we're going to do probably in the next couple weeks here is kind of shift gears a little less programming actually, a little bit more object-oriented concepts so that you can actually put together a design. And then fundamentally, you can go back and kind of say, well, how am I going to implement that? Well, you have to write, it's an interface class, and this is how you're going to put it together. So let's see, last note on the bottom here. So we only have single abstract class. It can implement many interfaces. Abstract class can have a partial implementation. It can be protected. You can have protected parts of an abstract class, static methods, and so on, because it's a class. It can actually have static methods. While the interfaces are limited to public constants, as we've seen so far, and public methods, and no implementations. So we got some limitations, actually. So it might depend on what your purpose is in terms of the design of the program. And let me rephrase that. Not really the design of the program. The program is writing the source code. It's the design of the object interface environment and this structured approach that you're going to take to this object-oriented methodology in this language that you're implementing. So that was a lot of stuff. I kind of feel like I went through it kind of quickly, even though I tried to go slow. But that's the interface, believe it or not, everything you ever needed to know about interfaces. And pretty short slide set, actually, but not bad. So what we're going to do, actually, is I'm going to start mixing in design theories and try to hopefully expose you to multiple different ways of thinking about the object environment. Because we are object-oriented design using Java. We're not a Java programming course, but we are programming because we're implementing it in Java. So as we switch gears in the coming next week, you'll notice a slight shift in less coding and more design, is what I'm saying. Are there any questions? I feel like I'm leaving. I feel like, well, I guess this makes up for the longer classes we've had. I feel like I'm cutting short. I feel like I'm missing something. No, we just ended this concept early. Or are you guys done? You want more? I can give you more. No? Do we want more? Oh, okay. All right. Well, then I guess we could call it quits for today. We had a short class then, maybe a half hour short. So take the time, go get a Starbucks or something. I don't know. Unless we have questions, I can entertain questions. I got some time. No, nobody's afraid to ask. All right. Actually, I'll spend the time now. We can stop the official lecture, and you can come up and we can troubleshoot problems and stuff. Everyone has Java installed. Oh, hopefully next week maybe I'll have an update. I don't know, do I have an update now on the I2 situation, the EMS? Is the class built? Oh, it's already in there? So we all know how to upload the assignments into the I2 EMS? But I have half the people leaving already because I said we were going to be done. Okay, I'll save that because we're getting a little loud. Huh? Oh, very good. Okay, very good. So, all right, come on up and ask me questions then. And then we're officially over. Thank you.